Let's explore the fundamental properties of a circle, one of the most important shapes in mathematics and our universe. Every circle has a center point, which we'll label as O. This point is equidistant from every point along the circle's boundary. The radius, which we denote with the letter r, is the distance from the center to any point on the circle. This is the key measurement that defines a circle. All points on the circle are exactly this distance from the center. The diameter is a line segment that passes through the center and connects 2 points on the circle. It's the longest straight line you can draw within a circle and always passes through the center point O. The circumference, labeled c, is the total distance around the circle. If you were to unravel the circle into a straight line, the length of that line would be the circumference. Now let's examine the mathematical relationships between these elements. These relationships hold true for any circle, regardless of its size. The first relationship is that the diameter equals twice the radius. This makes intuitive sense since the diameter spans the entire width of the circle through its center, while the radius only extends from the center to the edge. The second relationship is that the circumference equals 2 pi times the radius. Pi is that special constant approximately equal to 3.14159, which represents the ratio of a circle's circumference to its diameter. This means for any circle, if you divide the circumference by the diameter, you'll always get pi. These fundamental relationships will help us understand and derive the formula for a circle's area. Just as the circumference relates to the radius, we'll see that the area also has a special relationship with the radius. These properties, that the diameter is twice the radius and the circumference is 2 pi times the radius, are essential relationships that appear throughout mathematics, physics, and engineering whenever circles are involved. Let's start with a square, a shape whose area formula is familiar to most of us and will help build our intuition. When we measure a square, we label the length of each side as s. Each side has the same length, which is the defining characteristic of a square. To find the area of a square, we multiply its side length by itself. This gives us s times s, or s squared. This formula makes intuitive sense because we're calculating the number of unit squares that fit inside our larger square. We can visualize this area by filling in the square. Each unit of area corresponds to a 1 by 1 square, and we can see how these units tile the entire shape perfectly. Now let's transition to a circle, a shape with no straight edges or corners, making its area formula less obvious than that of a square. Unlike a square that's measured by its side length, a circle is characterized by its radius r, the distance from the center to any point on the circle's boundary. This single measurement fully defines the circle. But this raises an interesting question. How do we determine the area of this perfectly round shape using just the radius? This is more challenging than finding the area of a square because we can't simply multiply two straight sides together. The circle doesn't have any straight sides to measure. The circle's continuous curved boundary means we can't easily divide it into simple rectangular units like we did with the square. This curvature is what makes the circle's area formula one of the most elegant in mathematics, involving the special number pi. To discover the formula for a circle's area, we'll need to use a different approach that accounts for this continuous curvature. This will lead us to the famous formula, area equals pi times radius squared. Let's explore why the area of a circle equals pi times radius squared. This beautiful formula has a surprisingly intuitive visual explanation. We'll start by dividing our circle into 4 equal sectors. Think of it like cutting a pizza into 4 equal slices. Each sector represents exactly 1/4 of the circle's total area. Now, let's rearrange these sectors to form a shape that resembles a rectangle. We'll place them in an alternating pattern. First sector on the bottom left, second sector rotated at top left, third at bottom right, and fourth rotated at top right. Notice how these 4 sectors form a jagged shape that roughly approximates a rectangle. The height of this shape is exactly the radius of our circle, and the width is approximately half the circumference, which equals pi times r. With just 4 sectors, our approximation is quite rough. The jagged edges prevent us from getting an exact rectangle. Let's improve this by dividing our circle into 8 sectors instead of 4, which will give us a smoother approximation. With 8 sectors, we'll rearrange them in a similar alternating pattern. Each sector now covers a smaller angle, just 45 degrees instead of 90 degrees. This means each piece will have less curvature at its outer edge. With 8 sectors, our shape looks much more like a rectangle. The jagged edges are smaller, and the approximation is better. Notice that the height still equals exactly the radius, and the base still approximates pi times r, which is half the circumference. Let's improve our approximation even further by dividing our circle into 16 sectors. The more sectors we have, the smaller each piece becomes, and the closer our rearranged shape will be to a perfect rectangle. With 16 sectors, each covering just 22.5 degrees, our rearrangement will be even smoother. Each piece has very little curvature at its outer edge, making our approximation extremely close to a true rectangle. With 16 sectors, our shape is very close to a perfect rectangle. The jagged edges are barely noticeable. This rectangle has a height exactly equal to the radius and a base that's almost exactly equal to pi times r. As we increase the number of sectors toward infinity, the jagged edges completely disappear. Mathematically speaking, if we had an infinite number of infinitesimally thin sectors, our rearrangement would form a perfect rectangle with exactly height r and base pi times r. In the limit, as the number of sectors approaches infinity, we get a perfect rectangle with height equal to the radius and base equal to pi times r. This rectangle contains exactly the same area as our original circle. The area of this rectangle is simply base times height, which gives us pi times r, or pi r squared. Since this rectangle has exactly the same area as our original circle, we've proven that the area of a circle equals pi r squared. This elegant visual proof shows why the area of a circle is pi r squared. By rearranging the circle into a rectangle, we've transformed a curved shape into a familiar one whose area we can easily calculate. Let's explore how to derive the area of a circle using a powerful visualization technique involving concentric rings. This approach will help us understand intuitively why the formula is pi times radius squared. Instead of thinking about the circle as a whole, let's break it down into many thin concentric rings. This decomposition allows us to calculate the area piece by piece, which is much easier to understand. Let's focus on one thin ring at distance r from the center. This ring has a very small thickness, which we call dr delta r. The area of this thin ring can be approximated as the circumference times its width. The circumference at radius r is 2 pi r, and the width is dr. So the area of this thin ring is dA equals 2 pi r times dr. Now let's visualize the entire circle as a collection of these concentric rings, each with a different radius. Each colored region represents a ring with its own contribution to the total area. To find the total area of the circle, we need to add up the areas of all these rings from the very center to the outer edge. Since these rings become infinitely thin, we use calculus and integrate from radius 0 to radius capital R. Our integral is the sum of all these small areas, integral from 0 to r of 2 pi r dr. Let's evaluate this integral step by step. When we integrate 2 pi r with respect to r, we get pi r squared. We then apply the limits from 0 to capital R. Evaluating this between our limits, we get pi times r squared minus pi times 0 squared. Since 0 squared is 0, our final result simplifies to pi r squared. We've now derived the famous formula for the area of a circle, A equals pi r squared. This elegant result shows us that the area grows proportionally to the square of the radius. This result makes intuitive sense when we think about how the circle's area builds up. As the radius increases, both the circumference of each ring and the number of rings increase, creating a squared relationship between radius and area. These colorful concentric rings help us visualize how the area accumulates from the center outward, with larger rings contributing more to the total area due to their greater circumference. Let's explore a practical application of the circle area formula by comparing two different garden designs, one circular and one square. Here, we have a circular garden with a radius of 3 meters. The radius is the distance from the center to any point on the circle's edge. To calculate the area of this circular garden, we use the formula A equals pi times r squared, where r is the radius. This formula gives us the total space available for planting. Let's substitute our radius value of 3 meters into the formula, so we have pi times 3 squared. When we calculate 3 squared, that's 3 multiplied by itself, which equals 9. This gives us 9 pi. Since pi is approximately 3.14159, when we multiply it by 9, we get approximately 28.27 square meters of garden space. Now, let's compare our circular garden with a square garden that has sides of 5 meters each. Many gardens are designed in square or rectangular shapes because they're easier to plan and build. To find the area of a square, we simply multiply the length by the width. In this case, that's 5 meters times 5 meters, giving us an area of 25 square meters. For a clearer comparison of these two garden designs, let's rearrange them side by side. Here we have both gardens placed side by side with their actual proportions maintained. Although the visual representations are scaled down, they accurately show the relative sizes. The circular garden with its 3-meter radius provides approximately 28.27 square meters of planting space. This is the power of the pi r squared formula in action. Meanwhile, the 5 by 5 meter square garden offers exactly 25 square meters of area. Notice that despite having the same basic dimensions, a 3-meter radius versus a 5-meter side length, the shapes yield different areas. Interestingly, the circular garden provides about 3.27 square meters more space than the square garden. This demonstrates a fundamental property of circles. They enclose the maximum area for a given perimeter, making them mathematically efficient shapes. This practical gardening example illustrates why the circle area formula is so valuable in real-world applications. From garden design to engineering, understanding that the area equals pi r squared allows us to calculate space efficiently. Let's explore how the area of a circle changes as its radius increases. This relationship is one of the most fundamental concepts in geometry and has countless applications in science and engineering. We'll begin with a circle of radius 1 unit. The radius is the distance from the center point to any point on the circle's edge. The formula for calculating a circle's area is pi times radius squared. For our circle with radius 1, that's pi times 1 squared, which simply equals pi. We can think of this as our base unit of area. Now, let's examine a circle with radius 2 units. Notice how much larger this circle appears compared to our first one. When we double the radius from 1 to 2, the area becomes pi times 2 squared, which equals 4 pi. That's 4 times the area of our original circle. This is our first hint at the quadratic relationship between radius and area. Doubling the radius quadruples the area. Let's continue our exploration with a circle of radius 3 units. Again, observe how much larger this circle is compared to the previous ones. When the radius is tripled to 3 units, the area becomes pi times 3 squared, which equals 9 pi. The area is now 9 times larger than our original circle. This confirms our pattern. Tripling the radius makes the area 9 times larger. Let's organize these observations to better visualize the pattern between a circle's radius and its area. Looking at our results systematically, we can clearly see the pattern. When radius equals 1, area equals pi. When radius equals 2, area equals 4 pi. When radius equals 3, area equals 9 pi. These values correspond precisely to the squares of our radii, 1 squared, 2 squared, and 3 squared. This demonstrates that the area of a circle grows proportionally to the square of its radius. This quadratic relationship explains why even a small increase in radius results in a much larger increase in area. It's not a linear relationship, but rather a squared one. This pattern leads us to the general formula for the area of any circle, A equals pi times r squared. This elegant formula works for any circle regardless of size, from the tiny circles seen through a microscope to the massive orbits of celestial bodies. The formula A equals pi r squared connects the constant pi to the geometry of circles. Unlike the perimeter formula, which is linear with radius, the area grows as the square of the radius, reflecting how area is a two-dimensional measurement while radius is one-dimensional. This quadratic relationship between radius and area is what gives circles their unique properties in physics, engineering, and mathematics. Whether designing a circular foundation for a building or calculating the coverage area of a satellite signal, this fundamental formula is essential.